one, improper integrals had in infinite intervals. Type 2 improper integrals have discontinued integrand. So the integrand as a function has discontinuity, something like a vertical asymptote in the integrand. So we are looking at this integral. Actually, I should have said these because I put integrals here in plural. These integrals have discontinuous integrand. So here's a little graph to demonstrate that. Let's say we want to find, actually this will go like so, and let's assume that there is some kind of asymptote right there, a vertical asymptote, and we go from A, which is finite, to B, which B has a vertical asymptote, like so. So we're gonna integrate all the way to T. T, as we did before, T will be intermittent variable of integration. And what we'll do, we take the limit of T as T approaches B from the left side. Okay? So T is a moving boundary. So we're going to let T go closer and closer to B. So basically here we're going to say that T approaches B from the negative side. So meaning that we're going to use the limit as T approaches B from the negative side. Right? So what will be the result? Let's say if the area, let's say the area A, the area will be the integral. We want to integrate from A to B, so the definite integral from A to B of f of x dx can be written as the limit as T approaches B from the negative side, the integral from A to T of f of x dx. Pretty much the same idea what we used before when we had infinite interval. Okay, so as before, we need to have some definitions. We're going to have a couple of definitions very similar to type 1. So those are parallel. We're going to say first that if f continues, if f is continuous on the closed interval, semi-closed A, closed at A but open at B, okay, which implies that it's discontinuous at B. So we're going to write then the integral from A to B of f of x dx equals to the limit as T approaches B from the negative side of the integral from A to T of f of x dx. Again, if this limit exists. If the limit exists. Okay. And 2, if, I'm sorry, I missed the f of x here. I missed f, so here it should read if f is continuous. Okay. If f is continuous. Same for the second, and you can imagine what would be the next, I hope you can imagine what would be the next definition. If f is continuous, what would be the interval in this case? A will be open and B closed, correct? Then we're going to write that the integral from A to B, let me raise it up a little bit, of f of x dx, in this case it would be the limit as t goes to where? Any guess? Go ahead. A plus, right? A from the right. And the integral would be from t to b of f of x dx, again if the limit exists. So very similar, and likewise we can talk about convergent and divergent in a similar fashion that we talked about type 1. So we're going to say that if the improper integral, if the limit exists, then we have an improper, a convergent improper integral, and otherwise we have a divergent. Okay, so so let me add a statement here. Okay, type 2 improper integral are convergent if type 2 improper integral, let's change it to is convergent if its corresponding limit exists. And otherwise, it is divergent. As before, if you have discontinuity at C, then we can combine these together. If you remember, again, going parallel to type 1, we can go from interval AB, where C is a point of discontinuity in the middle. So we're going to say the following: if F has a discontinuity at B, at C, where C is a point in between A and B, like so, and both the integral from A to C of f of x dx and the integral C to B of f of x dx exist, then we have the following statement: the integral from A to B of f of x dx equals, remember C is a point of discontinuity in between, so it will be the integral from A to C of f of x dx plus the integral from C to B All right, so evaluate the integral from 2 to 5 of 1 over square root of x minus 2 dx. Again, the point of discontinuity is 2, so we are looking at definition 2, and as a result, we're going to say that the integral from 2 to 5 of 1 over square root of of x minus 2 dx, it will be the limit. Since we have the lower boundary, it will be t approaches 2 from the positive side. It will be the integral from t to 5 of 1 over square root of x minus 2 dx. Okay. All right, what about this integral? What is the result of this integral? If you look at simple substitution u equal to x minus 2, then you have the integral of 1 over square root of u, and the result is 2 square root of u, or the integrand, the antiderivative is 2 square root of x minus 2. So we look at the limit as t approaches 2 from the positive side of 2 square root of x minus 2, and we need to evaluate it from t to 5, right? So when you evaluate it, you come up with the limit, again, t approaches 2 plus, and you have 2 square root of t minus, 5 minus 2 square root of t minus 2, like so. And this will be 2 square root of 3, and here we have 2 times 0, so the answer will be 2 square root of 3. Okay.